All right. All 100%, right? Okay. Good. It's a lot easier to grade when they're just all right. Good, nicer. Okay, chemical differences between alkanes, alkenes, and alkynes. A few different ways you could go with this. If you got a few of them, I'll give you the 2 points. So first, what are some of the differences in structure?
Bonds.
Bonds. How?
Single bond, double bond, triple bond.
Yeah, single bonds, double bonds, and triple bonds. What about in reactivity?
Like negative charge for double bonds. Like that.
No, not really.
Somewhat negative.
Is it the more bonds they have, the more reactive they are?
Right. Those extra double, triple bonds, those can do reactions, can be reactive with other things. Single bond alkanes tend to only react in combustion. And there's a lot of energy present. And then what about shapes? What are the differences in some of the molecular shapes between these?
Tetrahedral.
Yeah.
Is one planar or something?
Mm-hmm.
And I don't know if the third one is.
Okay. Alkanes are tetrahedral, so kind of have that three-dimensional shape with the dash and the wedge. Alkenes, the double bonds, are flat or planar, have a flat trigonal structure, meaning there's kind of these triangle angles between them. And then alkynes are straight lines, linear. All right, those are the major differences. You could also talk about saturation versus unsaturation, that alkenes, alkynes will have fewer hydrogens per carbon. Those are the major things. You could talk about the bonds lengths. Double bonds and triple bonds are a little bit shorter. All right, let's look at these structures. So we've got cis-1,4-dichloro-2-butene. What does cis-2-butene look like? This was a question. Sounds like you guys were going back and forth on this one, right? So to figure that out, you make your double bond, and then you draw a line, an imaginary line through it, or a real line, whatever. I like to just kind of make a dotted line. And then you look at the two carbons on either side of that double bond, and what does cis mean? Same side or opposite side? Same side, right. So that means that those two bonds should be then on the same side of that dotted line. So that's what a cis alkene looks like. Trans would be the opposite, where you'd have this, and one goes down and one goes up. Now, it's not always nicely drawn straight in the middle like that. That's why the dotted line thing is nice, because no matter how it's angled, you can always see, are the other substituents on the same side of that dotted line or on opposite sides of the that dotted line for each carbon. So the rest of the structure then, that's butene. That's 4 carbons, 1, 2, 3, 4. And we need 2 chlorines on there to complete the structure. Okay. And then 1-ethyl-5,5-dimethyl cyclopentene. So we need a cyclopentene. Looks like that. And then we need to figure out how to count this. How do you number alkenes? Right, if you can, you go from the lowest. So lowest possible here would just be 1, because in the name it's not specified where the ene should go, so we can assume that it's 1, which means the alkene should be between carbons 1 and 2. And that means that there should also be an ethyl at 1 and 2 methyl groups at 5. Now, you don't need the numbers there. That's not really part of the structure. I just would throw that to show you how I numbered it. The black part is the structure. Is that what you've got? Great. Okay, and we got some naming. What's the main chain in this one?
Cyclohexane.
Right, cycloheptene. And again, we want to number it with the lowest number. So we're going to put a 1 here. Now remember, and this is what's tricky about this particular structure, if you say that the double bond starts at 1, then the other side of the double bond has to be 2. They always have to be consecutive numbers. So if the double bond starts at 3, it goes from 3 to 4. If it starts at 6, it goes from 6 to 7. If it starts from 1, it goes from 1 to 2, which means you're forced to number all the way around this way. So it's not 1, 2, it's 1, 7. Yeah.
Can you not number it with the one where the 2 is, and then it would be 2, 3 with the double bond starting at 1?
Right. If you put that in this case, I'll give you credit for it. Generally, the lowest possible number is what you go with. So having a 1 in there is 1, 7 is better than 2, 3 because 1 is lower than 2. But for this quiz, I'll give you that one. Yeah. So this would be 1 bromo, 7 ethyl cyclohexane. That was a tough one. Okay, what's the main chain of the next one here? Close. Let's count it out. 1, 2, 3, 4, 6. Yeah. So because the alkynes, and if you look at one of the examples we did in class on Thursday shows this, because the geometry is straight, you don't count the angles, you count the end of the alkyne. So you've got that triple bond, and where it ends, that's the second carbon. And we don't put it on an angle because its geometry is straight, is linear. So then this would be 3, 4 dimethyl hexine, or 1 hexine. That would be great. The other way you can tell there has to be another carbon there is that if this double bonded or triple bonded all the way to this one, there would be too many bonds to carbon here because it would be the triple bond plus these two, which is 5, which is too many bonds. So there has to be another carbon in the middle. All right. So that was the final quiz. Congratulations, you did it. You completed it. I don't know how well it went, but you completed it. All right, we just have a couple things. Oh, let me get your exams back first. As usual, you've got the multiple choice part on the front or on the top, and then the full scores on the other part. Go ahead and take a couple minutes to look that over. Today, with the rest of the time, there are a couple things in Chapter 11 we haven't talked about, so I want to make sure to mention those. It shouldn't take very long. And then if there's any time left, we can answer whatever questions you have on the exam or other topics that you want to talk about. Yeah.
I don't know if I got credit for this. I didn't know it was like
Yes, so I looked at your answers and I put them in, I believe. So if you look at your multiple choice thing, you should have answers to those. Like this says 30. But your actual score for that was 35.
Okay.
definitely make sure I've got my numbers right on there, too. All right, get a chance to look through that a little bit? You got yours the other day, yeah. Okay. Let's take a look at some of this other stuff. All right, so we talked about naming, we talked about this idea of saturated versus unsaturated. So the only thing we have to do now is look a little bit about the reactions. We talked about how alkenes and alkynes are more reactive than alkanes. We didn't really talk about what those reactions are. So I'm going to show you 3 different reactions that alkenes can do. We're just going to focus on the smallest alkene, ethylene. And then we're going to look at one other class of unsaturated compounds called aromatics. So ethene or ethylene can react with several different kinds of compounds. We're going to look at 3 examples. First, hydrogenation. What do you think that means? Yeah, we're going to look at hydration too. That's actually different. What do you think hydrogenation is? I'll give you a hint. It's the addition of something. Close. It's actually just hydrogen. So hydrogenation is just the addition of hydrogen. Hydrogenation. So we take excuse me. Thanks. We take our alkene and we add hydrogen, which is H2, right? A molecule of hydrogen is H2. And then that just adds to this. So we talked about how that was unsaturated. And that means that there's room for something else to come in if this is added. All right. So you can see it's a pretty simple reaction. This adds to this. Each hydrogen goes to a separate carbon, and that's addition of hydrogen. So you can see that we've converted here the functional groups because we've gone from an alkene, ethene, to an alkane. Right? In a line structure, hydrogenation looks even simpler because we don't account for all the hydrogens. So if you take something like trans-2-butene and you hydrogenate it, I should also note this usually has to use some kind of a metal catalyst like platinum or palladium. So that's also involved in the reaction. So if you take something like this and you hydrogenate it, what you're doing is adding hydrogen across that bond, and what you're left with is the alkene, or alkane. So it looks like, in that sense, it looks like you're just kind of disappearing the double bond. You're adding hydrogen to it, which makes it no longer an alkene. Now it's an alkane. So that's hydrogenation. Make sense? Kind of? If you go on and do organic chemistry. Okay, yes, you probably should. You can keep that.
That's an example.
Yeah.
Oh, I don't know.
You already took it.
I know, but I thought we would be granted.
Yeah. Do I usually collect the exam stack? Maybe.
I don't know.
Okay. No.
I'm just planning this semester.
I know. Nobody knows what's going on anymore.
Bye.
Bye.
Sorry to interrupt.
That's all right. Okay, so the next one we're going to talk about is hydration, which you mentioned. So if hydrogenation is the addition of hydrogen, what do you think hydration is? It's also an addition. Water. Yeah, it's the addition of water. So we're going to add water, and I'm going to write it a little bit differently here. Normally we would just write H2O, but I want to kind of show how it breaks up and adds. So we're going to write it HOH. And this also doesn't just happen when you mix these things together. It needs a catalyst. The catalyst in this case is acid. So you have to do this in the presence of acid. We'll just say H plus as some kind of acid. Could be sulfuric acid, could be whatever. And same kind of thing. We had HH, and each H went to a carbon. Now we have HOH. The H is going to go to one carbon, the OH to the other. So the H to one side, the OH to the other. And we've, again, used this reaction now to convert functional groups. We've changed the functional group from, again, an alkene to an alcohol. Because now it has that OH attached. In a line structure, that would look like this. So we'll use this structure again, this butene. And since we care mostly about the big molecules and what's happening to the big molecules, we often just write the reagents on the arrow. Since we don't write the hydrogens that are connected to carbons, that one doesn't show up, so it just looks like that. All right, and then the last reaction we're going to look at is called polymerization. This one's pretty different. In polymerization reaction, and in fact, alkenes aren't the only things that do polymerization reactions. There's a lot of different types of this, but this is a good example of one. We again take our ethene, or ethylene, and this time we react it with itself. So we just react many, many molecules of ethylene together and end up with a big chain. So we still have our ethylene unit, our C2H4, but we don't have that double bond anymore. And instead, the carbons fill their valences by connecting to other ethylene molecules. And so you can see kind of the individual ethylene units here connected to each other. Those individual C2H4 units connected in this long chain. And I just drew 3 of them connected together. But in this actual reaction, you'd have thousands of these molecules connected together, making an enormous molecule, just a huge, huge, huge chain. And this is what we call a polymer. A polymer is a very, very large molecule that's built from tiny molecule pieces. And those tiny molecule pieces are called monomers. So in this case, ethylene is the monomer. It reacts with itself a bunch of times to make a giant molecule called a polymer. Mono means one, poly means many. That's where those terms come from. And the polymers are named based on the monomers that they come from. So if our monomer is, it's actually known by its old name, ethylene, then our polymer is polyethylene. Polyethylene is a very common polymer. I think this is polyethylene. Yeah. If you look at the bottom of plastics, they usually have a little triangle with a number in them and then some letters below it, and that tells you what kind of a polymer they're made from. This one says HDPE, which is high density polyethylene. So it's that stuff. Milk jugs are also made from this stuff. A lot of containers. It can also get thicker and it can be used for things like all kinds of industrial equipment, tables, materials, things like that. The seats that you're sitting on, the foam is probably some kind of a polymer. The coating, the fabric is some kind of a polymer. The table is made of a polymer, probably with some wood inside it. The carpeting is made from a vinyl polymer like this. So these things are really important materials. They can be tuned in a way that natural materials really can't be. Like if you say, okay, this polymer is pretty good, but I want it to be a little bit harder, you can slightly edit that molecule and make that polymer a little bit harder. If you have some wood and you say, well, this wood is good, but I want to make it a little bit harder, you can't really do that. You have to find another kind of tree or something. So it's a lot easier to do with polymers. They're easy to manufacture. They can be cast. They can be shaped. So a lot of our materials now are made from polymers. All right. Okay. The last thing I want to talk about is this class of compounds known as aromatic compounds. Now, aromatic kind of sounds like something to do with smell, and that's originally where this came from, but now it has a pretty different definition. Aromatic compounds are related to this one molecule that actually becomes very important. So what molecule is that? This isn't the one yet, but what is that molecule? If that is a molecule, what would you call that? Well, that's what we're going to talk about in a second, but that is not benzene, actually. What is that one? That's one that we can name using our normal rules. Close.
Oh, cyclohexane.
Cyclohexane. Yeah, it's got 6. So that's cyclohexane. Now, if instead of having CH2s all around like that does, you use alternating double bonds in here so that every carbon only has one hydrogen. So now this is C6H6. That molecule is called benzene. And it's quite different from cyclohexane. Cyclohexane has a kind of a three-dimensional structure because of the tetrahedral carbons. This benzene is flat. And even though we draw this as double bonds, there's actually another version of it that looks like this. We could have drawn it this way instead. You see how those are just slightly different based on where I drew the double bonds? And those are the same, actually. So what that means is that benzene, actually, the double bond electrons aren't stuck between those two carbons, but they're shared around the entire molecule. So because of that, benzene is sometimes written, and I think it is in your book, with a circle in the middle to show that there's this sharing of electrons all the way around the molecule. And that makes it especially stable. Benzene is especially stable. And rings like this, these benzene rings, these aromatic rings as they're called, and things with other things connected to them, show up all over the place. They show up in your body. There's an amino acid, a common amino acid, phenylalanine, that has that in it. And molecules that have that structure can interact with most of the stuff in your body, depending on what else is connected to them. So you'll see most drugs have this kind of a structure in them because it allows them to interact with proteins and enzymes in particular ways. Everything from painkillers like aspirin and ibuprofen and acetaminophen to stimulant drugs to all kinds of stuff will have these types of structures. And so they're very, very common. The other thing to note about these is because they can interact with your body in such a way that a lot of these, when they don't have other groups on them allowing them to be metabolized, they kind of stick around in your body in not great ways. When you make these kinds of structures of a bunch of these things connected together, these kinds of aromatic compounds are carcinogens, meaning that they cause cancer. So not all aromatic compounds are carcinogens, like I said. A lot of medications and stuff have this part in them, and that's fine. A lot of foods have it, you know, no problem. But some of these larger aromatic compounds, especially when they're all connected together, and there's one, I'm going to change my picture just slightly. There's one that looks like this, that is actually a major cancer-causing component of cigarette smoke. When you burn things, a lot of these complex aromatic compounds get made in that smoke. And it's not just cigarette smoke, actually. When you cook meat over a fire or when you smoke meat, you're getting some of these kinds of things in your food as well. And that's why a lot of smoked meat can lead to things like stomach cancer. But these kinds of things are definitely to be stayed away from. They're called polycyclic aromatic hydrocarbons, or PAHs. And they're one of the major cancer-causing components in cigarette smoke, definitely tied to lung cancer. So a lot of different things going on, but you should be able to recognize aromatic compounds from these benzene rings and know what they are, that that's a functional group, and that they don't really do the same things as alkenes, even though they do have some alkenes. So when you see something like this, you know that formula is C6H6, not C6H12, like cyclohexane. You see the difference there? All right. Well, that's all I have to talk about. So what do you want to talk about now? You made it to the end. You learned everything in this class. Congratulations. True. All right. Any specific questions, or should I make up some stuff? Well, let's at least look through a couple things that some other people have talked about in terms of getting ready for the exam and studying. Certainly, here we can stop this.